Section: Introduction. In this section, we discuss the challenges of adversarial robustness in artificial intelligence, which has seen significant successes but still struggles in this area. Despite the impressive performance of image classification models on datasets like ImageNet, these models can still be misled by subtle changes to input images. Nicholas Carlini highlighted this issue, noting that despite thousands of research papers, progress has been minimal. The situation is similar for large language models, LLMs, which face attacks like jailbreaks, as they are increasingly used in various applications, exposing them to new vulnerabilities. As LLMs take on more agent-like roles, such as browsing the web or executing code, their ability to handle inputs from potentially untrustworthy sources becomes crucial. Just like ensuring self-driving cars operate safely, we must ensure that LLMs perform reliably to avoid harmful real-world consequences. Additionally, LLMs encounter unique challenges from adversaries who can manipulate the inputs they receive, such as embedding malicious instructions in messages. Currently, the best method for improving adversarial robustness is adversarial training, which involves training models to withstand known attacks. However, this approach is costly and relies on knowing the types of attacks in advance, which is often not possible. This creates a situation where developers are constantly reacting to new threats, akin to a game of whack-a-mole. We also note that while scaling up pre-training compute has benefited other AI tasks, it has not significantly improved adversarial robustness. In our work, we present initial evidence that increasing inference-time compute can enhance the robustness of reasoning LLMs, specifically OpenAI's O1 Preview and O1 Mini, without the need for adversarial training. Notably, this approach improves the model's performance across the board, unlike traditional methods that often compromise clean performance. Our contributions include proposing new attack strategies for reasoning models, measuring the robustness benefits of scaling inference-time compute across various domains, and identifying limitations where robustness does not improve with increased compute. We believe that focusing on scaling inference-time compute may help us better address adversarial challenges in the future. Section Summary. In this section, we highlight the ongoing challenges in adversarial robustness for AI, particularly in large language models, LLMs, where traditional adversarial training methods are limited and computationally expensive. We present initial evidence that increasing inference-time compute can significantly enhance the robustness of reasoning LLMs against various attacks, without degrading their performance on non-adversarial tasks. Section: Our results. In this section, we study various adversarial scenarios to measure how likely an attack is to succeed based on two factors: the resources available to the attacker and the amount of computing power used during inference. Our findings, illustrated in a figure and summarized in a table, show that for many tasks, increasing the computing power during inference lowers the chances of an adversary succeeding. This approach of enhancing inference-time compute is not specifically designed for adversarial situations. Rather, it generally boosts model performance. This contrasts with other methods aimed at improving adversarial robustness, which often compromise other capabilities. Focusing on the safety of large language models, LLMs, we examine tasks that require compliance with specific policies. These safety policies often have ambiguities that could be exploited. To better understand the impact of ambiguity and standard safety training, we concentrate on clear, well-defined policies, which we refer to as unambiguous tasks. For these tasks, we observe that as we increase the inference-time compute, the likelihood of an attacker's success diminishes. We also explore more realistic tasks with less clear policies, but our results here are mixed, as ensuring robustness in these cases is complex and only partially addressed in our work. We identify several necessary conditions for models to respond more safely in adversarial contexts. These include the model's ability to break down its context into distinct parts, the existence of clear safety specifications, the model's knowledge of these specifications, and its ability to apply them to specific situations. Our work shows that increasing inference time compute aids in applying safety specifications, even when adversaries present instances that differ significantly from the training data. However, we do not address the first three conditions, and our solution for the fourth is not yet foolproof. We acknowledge that fully addressing the challenge of adversarial robustness requires tackling all these aspects. We draw an analogy between legal systems and our work, where legal documents represent the specifications of the law, and judges enforce and interpret these laws. We evaluate how well language models, acting as judges, perform when given sufficient inference compute, while leaving the task of defining the law for future research. By focusing on unambiguous laws, we aim to assess the reliability of these judges without getting sidetracked by the complexities of ambiguous laws. Ensuring that the specifications for language models are comprehensive and account for edge cases is a significant challenge that needs further investigation. Our findings suggest that language models can perform better with more inference compute, marking a shift from their historical tendency to make unreasonable errors. We also note that inference-time compute has been previously used to enhance adversarial robustness in image models. Techniques like randomized smoothing have been employed to improve robustness by averaging outputs from augmented inputs. Unlike our approach, these methods require knowledge of potential attacks. Other strategies, such as test-time training, aim to improve model performance when there is a gap between training and testing data. Some studies have explored defenses against adversarial attacks, including paraphrasing, which can sometimes reduce performance. Additionally, research indicates that larger models may be slightly more robust without explicit defense training, although this effect is not consistent. Other works have proposed frameworks that enhance adversarial training by increasing both the dataset size and model capacity, leading to significant improvements in robustness. Section Summary. In this section, we explore how increasing inference-time compute can reduce the probability of adversarial attack success across various tasks, particularly focusing on unambiguous policy compliance tasks. We also highlight that while our findings suggest improved model safety with more compute, fully addressing adversarial robustness requires tackling additional challenges related to model understanding and safety specifications. Section: Experimental Setup. In this section, we outline our experimental setup. We explore various scenarios where a model receives a prompt, which is partially influenced by an adversary aiming to trick the model into providing an incorrect answer instead of the correct one. Our model belongs to the O1 family, and we adjust the amount of computational resources used during inference. It is important to note that we do not engage in adversarial training, nor do we utilize specialized prompting or defensive language model programs, except in our image experiments. We apply the same methods to enhance test-time computation that we use to boost the overall performance of O1 models. We assess the adversary's success based on two factors: the resources available to the adversary and the computational power during inference. We vary the tasks, the adversary's objectives, the types of resources they use, and the models we examine, specifically O1 Preview and O1 Mini. For each prompt, we take multiple samples from the model and calculate how often the model's response aligns with the adversary's goals to determine the success rate of the attack. Regarding tasks and adversarial goals, we focus on three types of mathematical problems: adding two-digit numbers, multiplying two-digit numbers, and a specific math task we call Math D. For each task, we consider different adversarial strategies, such as tricking the model into outputting a specific incorrect answer or slightly altering the correct answer. We also evaluate the model's resilience against adversarial attacks using the strong reject benchmark, which tests the model's ability to resist being coerced into revealing sensitive information. We analyze both the original and new types of attacks not included in the original benchmark. We refer to the original benchmark as strong reject, and the policy-violating questions paired with different attacks as misuse prompts. In this context, the adversary can input any text as long as the desired response violates policy. To assess compliance with our model's rules, we conduct an evaluation called rule following, where the adversary's actions mirror those in the misuse prompt scenario. We also adapt a task called simple QA, which involves challenging questions that require browsing for answers. The adversary's goal here is to manipulate the model into outputting a specific keyword. In the vision task, we use a model with visual capabilities to classify images, including adversarially altered images. The adversary aims to mislead the model into making incorrect predictions. We consider various types of adversarial attacks, including both white box and black box approaches. One method involves the adversary providing numerous examples within the prompt to achieve their goal, measured by the number of tokens used. We also test common jailbreaking techniques and soft token attacks, where the adversary optimizes embedding vectors to influence the model's output. Additionally, we employ human red teamers to find prompts that provoke policy violations and use an AI red teaming approach to discover effective attacks. We evaluate the model's performance against adversarial multimodal inputs, focusing on how computational resources impact the results. While we strive to make our attacks effective, we acknowledge that there may be even more potent attacks. Our assertion is not that these models are invulnerable, but that increasing computational resources during inference can enhance their robustness across various scenarios and attacks. Section Summary. In this section, we describe our experimental setup where we evaluate the robustness of O1 model family against various adversarial attacks, focusing on how inference-time, compute, and adversary resources influence the success of these attacks across different tasks, including mathematical problems and policy violations. We employ multiple attack strategies, such as many-shot and soft token attacks, while measuring the model's responses to assess their vulnerability and resilience without utilizing adversarial training or specialized prompting techniques. Section: Results. In this section, we elaborate on our results across different attack methods and tasks. Most tasks are assessed against all types of attacks, except for our adversarial website injection task, ADVA Simple QA, which has a unique structure and longer input. We will discuss this task in more detail later. For many-shot jailbreaking, MSJ, we exploit the model's tendency to follow few-shot examples by overwhelming it with numerous successful attack instances. We focus on the many-shot attack in mathematical problems, the misuse prompts task, and the rule-following task. In our analysis of the many-shot attack on math tasks, we observe a consistent pattern. As the attacker's strength increases, the success rate of the attack also rises. However, for any fixed resources, the success rate declines as the computational demands during inference increase. Interestingly, the success probability does not always increase with more computational resources. For instance, when the attacker aims to produce an output that is 7 times the original answer, we find that with very little computational power, the attack fails due to inadequate resources. Initially, we see an increase in success with more compute, but eventually, as the compute grows too large, the chances of success drop to 0. In our evaluation of the many-shot attack on the misuse prompts dataset, we find that the model's O1 mini and O1 preview show only slight vulnerability to the MSJ attack. We modified the misuse prompts to use past tense, as recent studies indicate that models are less likely to refuse such queries. Our findings suggest that increased computational resources during testing do not significantly enhance defense, particularly because the task is quite ambiguous. We categorize both misuse prompts and past misuse prompts as ambiguous tasks where additional compute may not be beneficial. We also applied the many-shot attack to the rule-following task, and our results are illustrated in our figures. Next, we tested against the strong reject suite, which includes 35 jailbreaks sourced from social media and previous research, along with a selection of misuse prompts. We narrowed this down to 60 prompts that breach our internal content policies. Our evaluation metric, goodness at 0.1, averages the goodness scores of the worst 10% of responses for each misuse prompt after applying every jailbreak. This approach simulates an attacker with prior knowledge of the most effective jailbreaks for each question. Our results indicate that increased computational resources significantly enhance the model's robustness. To mimic the iterative approach of human red teamers, we also conducted experiments using a language model program, LMP. In this setup, the attacker receives feedback on previous attempts and adjusts its strategy accordingly, continuing until it either succeeds or reaches a maximum of 25 attempts. This framework allows for a broader exploration of attack strategies compared to previous methods. We examined the effectiveness of the LMP in math problems, rule following, and misuse prompts, with results shown in our figures. Regarding misuse prompts, we assess the balance between defense and attack using the strong reject dataset. Unlike earlier sections, we do not directly apply strong reject attack methods. Instead, the attacker is prompted with a misuse scenario and tasked with devising any attack to extract relevant information. We then evaluate the defender's response to this generated attack using the strong reject grader. This setup blurs the lines between misuse prompts and past misuse prompts, as the attacker may opt for past tense phrasing if it seems advantageous. We find little evidence that increased computational resources improve defender robustness in this context, as the attacker consistently succeeds with few attempts. We attribute this to a mismatch between the strong reject grader and the defender's policies, rather than a lack of robustness, especially since the misuse prompts often seek dual-use information. Section Summary. In this section, we elaborate on our results from various attack methods, highlighting that many shot jailbreaking exploits model tendencies to follow examples, with success rates generally increasing with attacker strength but decreasing as inference time compute grows. We also find that our language model program approach allows attackers to adapt strategies iteratively, yet increased test time compute does not significantly enhance defender robustness against misuse prompts. Section: Soft Token Attack. In this section, we explore the concept of soft token attacks, where an adversary can manipulate the embedding vectors of tokens directly. The key benefit of soft tokens is that we can optimize them using gradient descent, which simplifies the process compared to other black box attacks we examined. Although this attack model is unrealistic since standard API access doesn't allow such control, we can still assess the potential advantages of test time computation and estimate the likelihood of an attacker's success. We find that when we vary the number of unrestricted soft tokens, the success rate approaches nearly 1. Our method for optimizing soft tokens involves splitting the dataset into training and testing sets. We sample responses from the model for the training problems while varying the inference time. For the pairs of prompts and chain of thought in the training set, we optimize the soft tokens to maximize the likelihood of the sampled reasoning followed by the desired answer. We then test the effectiveness of these soft tokens on the test set, again varying the inference time. During our optimization, we noticed that the norm of the optimized soft tokens increased significantly, sometimes exceeding 1,000 times the original norm. To address this, we introduced norm-capped soft tokens, which we adjust to maintain a standard embedding vector's average norm. However, this norm constraint may complicate the optimization process, making it harder to strengthen the attack. Our results indicate that, despite the unrealistic power of soft tokens, more computation time generally benefits the defender across most tasks. We observed that defenders struggle more when the core task is difficult, while the attacker's goal is easier. Next, we discuss prompt injection attacks in agentic tasks, where adversarial robustness is crucial. We modified simple QA by injecting adversarial instructions into the websites shown to the model. As expected, we found that increasing inference time computation improved resilience, often reducing the attack success rate to 0. In a more complex browsing scenario, we injected prompts into the last web result, and similar to the simple QA findings, the attack success rate dropped to 0 once the computation exceeded a certain threshold. We also examined multimodal attacks involving vision inputs. We focused on 2 adversarial image datasets, ImageNet A, which contains natural adversarial examples, and Attack Bard, featuring images generated by transfer-based attacks. The adversarial modifications were optimized for Bard MLLMs and were transferable to other models like GPT-4v, achieving a 45% success rate. We also tested the non-adversarial version of Attack Bard, providing class label information in our prompts. In our experiments, we evaluated the O1 series model, capable of processing visual inputs, to predict the class label of images. An attack is deemed successful if the model makes an incorrect prediction. As with text-only tasks, we found that increasing test time computation generally improved the performance of the O1V model across all datasets. Notably, it enhanced robustness against adversarial images and also improved performance on clean images. Overall, our findings suggest that increasing test time computation strengthens the robustness of the O1 model in various scenarios, and further research into the adversarial resilience of multimodal models, especially against stronger image attacks, is a promising avenue for future work. Section Summary. In this section, we explore the concept of soft token attacks, which allow adversaries to optimize token embedding vectors directly, leading to high success rates in attacks, especially when given more inference time. We also investigate the robustness of multimodal models against adversarial attacks, finding that increased test time compute generally enhances model performance and resilience across both text and image tasks. Section: Human Red Teaming. In this section, we conducted a red teaming campaign on O1 Preview to assess how increased computation time during inference affects model robustness. We had 40 red teamers carry out attacks across 5 different levels of inference time, focusing on refusal or safe completion policies in 4 main content areas: erotic content, illicit behavior, extremist content, and self-harm. To maintain unbiased results and consistent effort, we used blind and randomized testing, keeping the inference time levels hidden from trainers and randomizing their order. We also rotated trainers to introduce varied attack strategies. The red teaming process was split into 2 phases. In the first phase, called prompt generation, red teamers generated 20 effective prompts for each inference time level, resulting in a total of 100 prompts. We reviewed successful attacks to ensure they were diverse and impactful. We measured how many attempts were needed for the red teamers to achieve a violation, with a higher number indicating more robustness. In the second phase, application evaluation, we applied the successful prompts from the first phase to the other compute levels, totaling 80 prompts. This helped us evaluate how effective each attack was when applied at different inference times, with a lower number indicating more robustness. We also introduced a novel attack on reasoning models, which we call the Think Less attack. This attack aims to reduce the computation the model performs during testing, making it more prone to errors. We explored one version of this attack that we discovered through our red teaming efforts. We tested the Think Less attack across various tasks using a setup with 64 examples, which is enough to compromise the models when computation time is low. Our findings showed that O1 Preview is significantly more robust against this attack compared to O1 Mini, although other prompts might still deceive O1 Preview. From a defensive perspective, the Think Less attack is advantageous because it can be monitored. We can flag instances of unusually low computation time. It's possible that some of our other settings might effectively be a Think Less attack in disguise. While we found that robustness generally increases with longer thinking time, we also observed that the distribution of inference time does not change much during the attack, and in some cases, it even increases. We also identified a failure mode in reasoning models that we call nerd sniping. This occurs when the model spends excessive time reasoning beyond what is typical for a given task's difficulty. These unproductive thought processes can lead to higher attack success rates. Our data indicates that for most levels of requested inference time, the success rate of attacks is higher for instances in the top 5% of computation time compared to the median. This suggests that while allowing more computation time generally improves robustness, it can also lead to unproductive reasoning. This presents a new avenue for attacking reasoning models by encouraging them to waste computation time on unproductive tasks, similar to the Think Less attack. We must consider these strategies to ensure that attackers cannot manipulate the models into ineffective reasoning.